Having designed a very simple air filter for my bedroom, a silent one, I thought I would get one of the commercial ones, but with the biggest air filter I could find inside. And I'll show you this. I'll just pop the cover off. It unclips like this, slides off, and reveals this big HEPA filter. And this particular unit came from eBay, and the whole unit with the filter cost £16, which was pretty good, but the price was variable. It was either £16.20 or one listing was for £35. However, it does recommend changing this filter once every 6 months minimum, and the cheapest filter I could find was £17.50 from a random online shop, but on eBay it was £30 for the filter, which is approximately double the cost of buying the whole unit with a filter. And I get the feeling, is this a loss leader? Are they trying to get you into their cycle of buying their expensive filters? Is this going to be one of these things that, basically speaking, oh, I'll just turn that back off again, it's making squeaking noises. Is this one of these things that they're going to basically, people are going to buy it, realise how much the filters cost when it comes time to replace it, and then they're just going to put it in a cupboard or sell it on eBay and say, filters should be good for a wee bit longer, etc. Yes, I saw plenty of stuff being sold like that. I'm trying to get this cover back on. The cover is not going back on. Oh, this isn't going well, is it? Oh, there it goes. Anyway, right. Let me turn it on and let you hear it. So it's got a LED to indicate it's on. It's got a USB connector. You press the button. Do you hear that? Did you hear it starting up? It's pulse width modulation. It's got 2 speed settings. You either have the low speed setting, which has that whine in the background, or you have the marginally higher speed setting, which has less whine, but it still has whine. It's pulse width modulating it, and that is coming across a tone. I wouldn't actually want this in my bedroom. This is noisy compared to the one I cobbled together out of the computer fan. This is the problem with small fans. But anyway, let's take it apart. We'll take a look at the filter. And the filter is this pleated paper. Zigzagged. I don't think it's sealed at the edges. Is it sealed at the edges? What's sticking it together? Is it glued? Not really sure. Some of the other filters I've seen are filled with resin. I don't think this is filled with resin though. It might be glued in. But I see a little ledge there that could almost bypass air. But inside is, that beyond this pleated filter, there is this active carbon filter inside. It's quite coarse. It's just a very coarse filter, just designed for odour removal, I guess. I have measured the depth of these pleats. They're roughly 5mm, so every single one of these represents 1 centimetre. There are approximately 110, so this is equivalent of 1.1 metres of fabric, and that is the equivalent of about just over a metre of the tissue that I was using on my sort of strange DIY prototype one. This one says change between 3 months to 6 months. If you're doing that, keep in mind that I was going to basically change the filter paper every week. It would actually work out, well, not only more cost effective, but it would actually result in a greater surface area over that period of time. This has a decent airflow though. That's got to be said. Right, tell you what, I'm going to put this out of the way. Even if it comes at the cost of noise. Let's take a closer look at this. I see this top looks like it clips in. Does it clip in? Am I about to burst it? I don't see any screws. I think this is going to pop out. I don't know if the top is supposed to be quite as flat as the syrup's been. Oh, it is. It's plastic. I thought that was a metal mesh. It's a sort of honeycomb mesh. Inside we have a little computer fan. Oh, it says maximum power. It runs at 5 volts. It's USB. It says maximum power 4.5 watts. I measured the low at 140 milliamps. Let's bring in the kink calculator and just do that. 0.14 times 5. Low power was 0.7 watt. High power was 210 milliamps. 0.21 times 5 volts equals, it's 1 watt. So it's not really that high a power. It's very similar in a way to the computer fan I used. I'm guessing it is just using a butchered computer fan. This may clip on. or not. Does this label got any screw holes underneath it? No, I think it's just covering a mould hole. What about these feet? Hold on. Oh, it's got little pillars inside. So if I get these feet out, hold on, let's get the screwdriver in and gouge those feet out. Yeah, there's a screw under them. What am I expecting? What are we expecting in here? I'm expecting one transistor. One transistor for the motor. And a little 8-pin microcontroller as usual. I mean, it's just so common that you get that arrangement. And the LED is not very bright. It's being driven. It is controlled, so it'll be being driven from one of the pins of the microcontroller. And after that is a button, and that is it. I wonder if it does anything nasty, like, you know, after a month it starts flashing a light and refusing to run or something like that until a new filter's put in. I don't think so. I think it just relies on people changing the filter after a period of time. The eBay was absolutely full of people selling old units, either without the filter because they'd discovered how much the filters cost or they couldn't get them, or with the filter saying that loads of life left, which is probably a bit of a porky. Oh, this is not coming off. Oh, it is coming off, but it's going to require a bit of force. Yeah, it's clipped on. Ooh. What's that? Oh, that's a weight. Is that just a weight in the bottom? I think it is. Hold on, let's unscrew it. I can see the circuit board here. Oh, I can see 2 transistors in the circuit board. That's not expected. Unless one's a voltage regulator. We shall whip the circuit board out and take a look at it. Yeah, I think this is a weight, just to weigh it down and stop it sliding about on the table. It's a weight. Oh, they didn't mention that. It's got an ionizer in it. It's got a little ionizer module sticking about here where it can't really do... Oh, shit, that's just... What? That's useless. Oh, it's not positioned correctly. They've jammed it in. It's just utterly pointless in there. But it's got an ionizer, which is useful. That's what the other transistor's for, isn't it? Right, tell you what. Let's get this circuit board out. I don't remember it mentioning ionizer. Maybe I should have read the manual. I would want the ionizer thing actually sticking out. It's got a little channel here that it could have done that, but yeah, because it needs airflow in there. Ah, very strange. Very peculiar. Kind of, I'd want it, you know, sticking out roughly through the side into where all the air's coming in. Very, very odd. But it is what it is. Things can be modified. We have the 2 buttons. We have the... Odd, it's not an 8-pin chip. Right, tell you what. You know the script. I'm going to... oh, there's 3 transistors. What the heck? Okay. One moment, please. The reverse engineering is complete. Let us explore the design. The USB supply comes in over here and immediately gets hit by 2 decoupling capacitors. One will be low value, one will be higher value. The reason is just provide filtering and provide a local buffer just for stability of the circuitry, but it's not very good because one of those should be over here next to the microcontroller, particularly when loads are actually sharing the same current path as the supply rails to the microcontroller. But I digress. Let us continue. Here is a microcontroller and it's got 2 buttons, the position for a third one, and they lead back. I've color-coded it, yellow to this pin, yellow to this pin, yellow to this pin. So they feed back straight to the pin. So they'll have internal, what they call pull-up resistors set inside this chip. And when you press the button, it'll actually go from a high to a low state. The supply rails for the chip are in the middle, which is fairly common for microcontrollers. We get the negative at this side in blue, positive at this side in red. The reason I don't normally use black is just because the blue is clearer for the negative. I've marked all the positive pads in red, the negative pads in blue, and the switched negative in light blue here. Other things worthy of note. Really strange circuitry over here. It's designed to drive ultraviolet LEDs. It has a switching control chip that can switch an inductor and then go through a diode to actually drive the LED and then get sent through the chip. So it's a dedicated fixed current switch mode chip. That is switched by presumably a MOSFET, owing to the fact that there's a resistor position here that is just linked across. So this pin here can theoretically pull a P-channel MOSFET to ground and turn it on, and that just basically turns on this whole little switch mode current regulated ultraviolet circuit for the future when ultraviolet LEDs become available, or maybe they just use a little potted module like this driving a little UVC tube. The ionizer, it's a problem. It's a huge problem actually. It's a slightly scary problem. There are 3 transistors. One controls the ionizer, which is not going back into the unit, and the others control the fan, but I was wrong. It's not got a switch on power supply. No, that's wrong. It's not using pulse-width modulation. I'm just thinking ahead of myself there. One transistor, this one, is the high mode, and it just basically brings the fan on at full power. If the low mode transistor comes on, it powers the fan via a Schottky diode and a standard sort of 0.6 volt silicon diode, and it just introduces, basically speaking, they left their options open. They could have used 2 silicon diodes. It just drops the current, the voltage effectively to the fan, and that lowers the current. Other than that, the LED has a really high value, 4.7K resistor, which is just driven directly by the microcontroller. And the transistors are just standard NPN transistors with a resistor each, but 2 of them are 510 ohm and 1 is 1K. I'm not sure why that is. It's all rather odd. I'm guessing the middle button is for enabling the ultraviolet feature. Okay, or actually, you know what? There's a separate transistor for the ionizer, so maybe that was actually to switch the ionizer on and off. I don't know, strange. It only seems to have 2 modes, high and low, and on and off. Here is the schematic. Let us explore it. The supply comes in. There's the 2 capacitors. I'm going to make a wild guess. 10 microfarad and 100 nanofarad. That would be typical values of those. The 10 microfarad would be the sort of buffer one that keeps us a fairly stable reservoir of energy locally, and the 100 nano is designed to react fast. It's got very low impedance, so it can handle spikes and glitches and suppress them. There's the microcontroller. There's its 3 buttons pulling to the 0 volt rail. There's the LED with its unusually high resistor, which means it glows very dimly. It's connected to the positive rail, pulled low by this 4K7 resistor. There are the 3 transistors, one driving the fan on completely with its 1K resistor for the base. The other transistor there, switching the fan via these 2 diodes, just forward bias diodes, so that you'll drop, say, around about 0.2 volts and roughly 0.6 volts, maybe a bit higher, particularly under higher load, but typically dropping 0.8 to 1 volt-ish, roughly. So that just makes the difference between the fan at low and high settings. That high-pitched whistling noise from the fan must have been the fan's own drive circuitry, particularly just as it was starting up, it would make that whistling. It was just its built-in circuitry. Then we've got another transistor switching the ion module, which only draws 16 milliamps, and I've tested it. I can prove it. Let's power the ionizer up. I shall bring the meter in and prove that the ionizer works. An ionizer creates a high voltage reference to ground. I have to mention that because some people will not be regular viewers of the videos. Regular viewers will be sick of ionizers because I feature them quite a lot. Too much. Let's get this on. Let's stand this little module up. If I can stand this little module up, it's not wanting to stand up. So I'm going to get these leads for the meter. I'm going to turn the ionizer on. I'm just going to untangle my leads first. And the negative lead is going to be grounded. So I'm turning the ionizer on now. It's drawing its 16 milliamps. I put this lead in front of that little bunch of carbon fibre bristles, and just hovering in front, the voltage with reference to ground goes up to quite high voltage, about about over 6 volts if you get close enough. I could go even closer, but there is a risk it's going to start zapping things. I'm not going to leave that on too long, because there lies the problem. I've just turned it off. The way an ionizer works... Oh, my stomach is making bubbling noises. My apologies if that's coming across. Oh, do you know what else I should have done? I should have shown what the fan's capable of if it's just powered up directly. So let's get this crocodile clip onto there, and this crocodile clip onto here, and then keep my fingers well clear of the fan blades, and grip the housing. That should do it. Not too loud, not too bad. Oh, I could almost be tempted just to leave that on at full power. 400 milliamps, just under 400 milliamps. So that is the sort of what they suggested that the fan might draw, but the circuitry and the cable probably limits that. So what's the problem with the ionizer? If you use a standard USB power supply with the non-earth power supply basically, and it's not got any reference from the output to the input other than just a capacitance, you end up with the situation that you've got your live to neutral going in. The live and neutral are by default. The neutral is effectively referenced to ground. But you have the switch mode power supply drives the primary of its little tiny transformer inside. And the secondary is completely isolated. And the only other thing connecting the two of them is a class Y capacitor to provide because there is an element of capacitive coupling between these. It provides a route back and it just reduces interference, but it also shows that slight tingle you sometimes get off a charging phone. The secondary side is a low voltage. You've only got about 5 volts here. It's got the diode for rectification and it's got the smoothing capacitor. Then it goes to feed the ionizer. The ionizer then steps that up to a really high voltage, let's say 4 kV, and that creates but it's a negative 4 kV, and it has this bunch of tiny little carbon fibre bristles. It used to be needles, but they've gone for the carbon fibre bristles because they're extremely conductive and they're extremely fine and they're just perfect for the job. And that imparts an electrical charge onto the air, imparts electrostatic charge, which then gradually fills the surrounding area, and it charges up dust particles and things, and then they precipitate out. Because this is negative, the other end of it is positive. It effectively precipitates out to the walls and floors, but there's a problem. This end of the high voltage ionizer is positive with respect to that one, but there's no reference to ground. This end should be grounded to actually operate properly, but because it's not, you end up the very high voltage across the transformer that's wanting to get back to ground, and that can result in insulation breakdown. Some of these power supplies have a little set of high voltage spikes on the circuit board, little tracks, to actually allow a spark to jump across. Others, and this is the best option, they have a chain of resistors going from one side to the other, and they use a chain of them just to get the high voltage rating of that. But they provide a current path back, and that would be perfect. That would be great for these ionizers, but most of them don't have that, which means the voltage builds up until it sparks across somewhere, and that could actually break down the insulation in the windings. And when it breaks down the insulation, it forms a conductive path at that point. And after you've used a power supply with an ionizer like this, and this includes a little 12 volt DC ionizers, if you've used a power supply like that, there's a risk that the primary secondary insulation has been damaged and it could actually pose a shock risk in the future. It's worth considering if you ever have to power one of these little ionizer modules, or even the ozone modules. They're not so bad, the ozone, because pretty much the output of the ozone generators, it just comes out and it forms a sort of capacitor with a dielectric. So it doesn't do that, so if it doesn't create much of a voltage gradient in the vicinity. But the ideal thing to do with these is the negative side, actually connect it to the incoming supply's ground, because that's the safest thing to do. It means that it does have a route back to earth and it's not going to put the insulation under stress. Someone sent me a video a while back. I wonder if I've still got that somewhere. And it was the circuit board, and they had it connected to an ionizer, and they showed the picture of the back of the circuit board because they heard a clicking come from it, and you could see a distinct spark going tick, 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 jumping from the high voltage side to the low voltage side. So that's worth considering. So, the synopsis. The synopsis about this thing. The circuit board design isn't great. That decoupling should be closer to the microcontroller. It means it could potentially crash, it could make it unstable. But it does kind of work, I guess. The ionizer is a terrible thing. The ionizer wasn't even... The way it was mounted in the case, the ionizer was basically just stuck up against the plastic. And if I could just grab that. More than that, it was actually it was laid in like this. And then the actual fibre brush here was... I'm just going to brighten this image up a little tiny tad. The fibre brush was actually just pointing at this wiring, which isn't great because it will eventually kind of just spark onto that wiring, could actually cause other issues. It could kill the LED, it could upset the circuitry, it could crash the processor. But ideally, this little carbon fibre should have been out into the airstream. I'm not sure why they did that. Maybe they actually want to take it out there, but you don't mix high voltage with low voltage. You don't port them through the same bit. It's very strange. It's not a great design. That is not going in. There's too many problems. They've just stuffed this in as an optional extra, much like they're intending to do with the ultraviolet. But other than that, I suppose it does work if you can accept the fact that the cost of the unit, once its filter is depleted, you're pretty much going to have to pay the same again just to buy a replacement filter, and you might as well just buy a complete unit. It's not great, is it? That's why Dr. Claire's patented toilet paper filter is much better. But there we go. It was interesting to take to bits. I will reassemble it. I may use it for a while, I guess, although it's quite noisy. I'm wondering if I should just bypass the control, and just when you plug the USB lead in, it just runs at full power without any inhibition of shitty circuitry. Not much in the back, incidentally, just a ground plane. But, yes, the synopsis is that it's interesting, but it's not terribly well designed. And the filter is an issue because the replaceable filter is basically, this may be a loss leader, and they're going to make their money in the filters later on, which means you're probably going to just stuff it in a drawer somewhere and not ever use it again. Or stick it on eBay and sell it as slightly used.